Just a second. Our next speaker is Agustin Silva, right? Am I right? And he will be telling us about the testing of the cosmological principle in a quantum universe. So, please.
I know it's Friday, so please bear with me a few minutes. I will tell you what I've been doing with my supervisor, Renate Lol. And this talk will be following the lines of a previous talk, Beglok, who said that we should be asking the proper questions to our quantum gravity theory. And he said that we should be asking, does your theory provide an emergent universe that is of cosmological type? Does your theory provide emergent symmetries? And we will be focusing on asking to causal dynamical triangulations if the theory actually provides an emergent universe with some emergent symmetries. In particular, we will be asking if the emergent universe coming out of causal dynamical triangulations is isotropic and homogeneous. So, first the outline of the talk. I will first briefly introduce what causal dynamical triangulations is and why we want to study it. Then later on, I will focus most of the time of the talk into defining what homogeneity is and how to define a quantum gravitational observable capable of quantitatively testing the inhomogeneities of an emergent spacetime. And if I have time left, I will also focus on explaining what isotropy is in these kind of emergent universes and how do we define observables for that. Even though it's the one I'm most interested about, I have a very limited amount of time, so I probably won't be able to do this. And then, of course, my conclusions. So, what is causal dynamical triangulations? Briefly speaking, it's a lattice version of quantum gravity. So, since it's very difficult to do, and probably impossible to do analytical calculations in a full path integral of quantum gravity, you go numerical. So what you do is you discretize the spacetime in a particular way. You can use different types of building blocks. They are actually relevant in the continuum limit, but for simplicity, one uses simplices. And in causal dynamical triangulations, one replaces the full path integral of quantum gravity with a sum over all possible simplicial discretizations of a manifold. And the beautiful thing is that when one does this discretization, one discretizes the Euclidean Einstein-Hilbert action, and the Einstein-Hilbert action takes this very, very simple form that depends only on the number of building blocks that you're using. This is in 4 dimensions, so it depends on the number of vertices, on the total number of 4 simplices that you're using, and some coupling constants that are related to the cosmological constant and the Newton coupling. And the beautiful thing is that this simple action is independent of coordinates. So by definition and by construction, the theory is diffeomorphism invariant. Now, the problem is that, again, we don't have coordinates. So there is no tensor calculus in these geometries, and if we want to extract geometrical information about these emergent universes, one has to rely only on 2 tools that are well defined in these universes, which are distances, geodesic distances that you can measure in these quantum geometries, and volumes, that you can also measure volumes. And nothing else, because this is for an example of a path integral configuration of a 2-dimensional causal dynamical triangulation that you can embed in 3D, so I can show you this beautiful plot. But it's extremely fractal and non-smooth. So this has no hope of defining a tensor calculus in it. So if you want to do calculations, as I said, you can only rely on distances and volumes. All right, so why causal dynamical triangulations? As mentioned in some previous talks, there is a phase space in this, in the parameter space of this theory, and there are some phases, and there is a particular very interesting phase which is called the de Sitter phase that has the beautiful property that even though the configurations of the path integrals, as I said before, are extremely non-smooth and fractal, they somehow conspire to give rise to a universe that has this shape here. If you put the spatial volume on one axis of the universe and as a function of the time, it fits a perfect cosine cube shape. This means this is the Euclidean version of a de Sitter universe. So somehow these very fractal configurations conspire to give rise to a de Sitter-like universe, and we want to study this universe. I want to emphasize that on the beginning, no one ever assumed any symmetry or any background. This is background independent, and we did no assumptions on the symmetries. And this directly comes out of the numerical analysis of the full non-perturbative party integral of quantum gravity, which I believe is amazing. And we want to construct observables to extract the geometrical properties of this emergent universe. We want to know if this de Sitter universe is actually related to our universe. And in particular, we want to study homogeneity and isotropy. Now, the questions we want to address are, so can we, using this emergent de Sitter-like universe, somehow justify the usually assumed initial condition of our universe as an isotropic and homogeneous exponentially expanding universe? And therefore, does this emergent universe satisfy the bounds in inhomogeneities and isotropies, for example, for inflation to happen? To answer these questions, we need to construct quantum gravitational observables that are capable of testing quantitatively if the emergent spacetime is inhomogeneous or anisotropic. So let's go to the basics, because we will have some difficulties. I will build the observables together with you. So this, for homogeneity, one has to go to the definition. So a homogeneous space is a space that has translation symmetry of all its properties. Now, this has some difficulties because there is no notion of group action in these very non-smooth geometries. And as I said, there is no tensor calculus. How do you apply a translation if you don't even have coordinates? And also, this is a very restricted definition. In physics, symmetries, like, for example, translation symmetry or isotropy, they can emerge at certain scales. So we need to have a definition that is scale-dependent. If you're going to test symmetries, it has to be in a scale-dependent manner. And symmetries might emerge at different scales. So we will use a more statistical definition of homogeneity, and also we will not use any group action. We will only use a distance measure and a volume measure, which is all we have in this causal dynamical triangulations approach. And we will define observables that are capable of testing this symmetry, as I said, in different scales. To do that, we will take ideas from astronomy. So in astronomy, if you want to know if our universe is actually satisfies the cosmological principle, what you do is you pick a chunk of the universe, which is, for example, this box here. This box has a certain size, and then you pick a property, which can be, for example, the distribution of mass inside this chunk of the universe, and you take the average of this property, and then you compare this average with other chunks of the universe, right? You make a comparison, a statistical comparison. And then if this coarse-grained property in this chunk of the universe is the same everywhere else, then you conclude that, for example, the universe is homogeneous and isotropic. In our case, our universe seems to be homogeneous and isotropic at scales above 300 megaparsecs, but not below. So this is a symmetry that is scale-dependent. And we'll try to apply this in a covariant way to quantum gravity. But exactly this is the idea that we want. Our definition of an homogeneous space is going to be that of a space looking the same everywhere and at different scales. So, as I said, we want to do this covariantly and using the only two tools we have. So our chunks of the universe, if you have an emergent universe like in CDT, is going to be a geodesic sphere. So we pick a scale, which is going to be the radius of this geodesic sphere. We pick a property, which we will call Q of x. It's a local property. It can be the scalar curvature. It can be the temperature. It can be a scalar field, whatever. And then you coarse grain this property in this chunk of your universe, which is going to be a geodesic ball. And you will compare this geodesic ball in a certain way with different regions of space-time. So to introduce annotation, as I said, we define geodesic balls as all the points that lie at a certain distance from the origin. So x is a point in the space-time. We know how to measure distances, so we know how to create geodesic balls. This is a notation for the volume of a geodesic ball, which we also know how to do because we simply count the number of elements at a certain distance. And then we define the coarse-grained property, Q of x, as simply the average of a property inside its geodesic sphere at a certain scale delta. Remember that this delta is just the radius of the sphere. The larger the radius of the sphere, the more coarse-grained your property is. Now, of course, if you want to make a comparison of a certain coarse grain property, you need a reference value. The canonical reference value is the mean value. So we take the mean value of this coarse grain property in a given manifold, M, which is one of, in each of the part integral configurations, each of them is a different manifold. And we take the average of this coarse grain property, which, as I said, can be any scalar property that you can measure. Sure. Naturally, you have an observable that quantizes statistical deviations, which is a standard deviation. So you can measure the standard deviation of this coarse grain observable over all the manifold. And if you take the quotient of this standard deviation with the mean value, then you have an observable, which is a point-independent scalar, scale-dependent, because it depends on the scale, on the scale delta, that gives the numerical value of this observable is a percentile deviation from perfect homogeneity. So if you put this into your part integral and you choose a given quantity q, then this will return a number telling you, hey, your ground state of your part integral or your emergent universe is a certain percentage of, has a certain percentage of inhomogeneities regarding this property. So this is what we do. We put this observable inside a part integral in our causal dynamical triangulations, and the resulting numerical value is going to tell us percentile deviations from perfect homogeneity. We can do this in two-dimensional CDT. We can also do it in four-dimensional CDT. Unfortunately, I'm really bad at coding, so I only have a code for 2 dimensions. But in the future, this will be applied in 4 dimensions. But as I said, this is a configuration in two-dimensional quantum gravity. And then you can also do the same. You can construct geodesic spheres, coarse-grain a property, and compare this property in different regions. So if one picks, for example, the scalar curvature in these geometries, one can apply this to our observable and obtain numerical values. These numerical values are in this axis, and in this horizontal axis you have the scale. So the larger your scale is, this indicates that it looks every time more homogeneous. In the case of two-dimensional quantum gravity, which is just a toy model, I'm not claiming this is something physical, but it indicates that in the continuum limit of this two-dimensional model, you get 20% size inhomogeneity. So the fluctuations are 20% of the mean value, which is quite large. So this indicates a very inhomogeneous continuous limit. So I have how many minutes? 3? Yeah, OK. Then I will just briefly sketch how the story with isotropy is. So we can also develop observables that give you a quantitative answer to the question, is your universe isotropic or not? The thing with isotropy is a bit harder, but the main idea is that instead of looking at homogeneity in the whole space-time, you can just start at a point here, this point, and look at a certain celestial sphere around you and look at homogeneity on this sphere. This is basically what we do here on Earth when we look at the CMB. We just have a certain sphere, and we look at if it is homogeneous or not. Well, you can do exactly the same procedure in these quantum geometries, and you can compare in these spheres here on top of your celestial sphere. You can do some statistics and look if it's homogeneous or not. So if it's homogeneous, a certain property on a sphere, then it means that it's rotationally invariant, and therefore it is isotropic. The observable itself is too scale dependent. Now you have a scale, not only your coarse grain is scale, which is the scale of the size of the chunk of the universe that you're choosing, but also you have the distance at which you are looking at your celestial sphere. So you have 2 scales, delta and epsilon, and you can make, well, these beautiful plots that will tell you a number of how anisotropic your universe is. In the case, of course, of two-dimensional quantum gravity, you can just make these 2 plots, this is the size of your celestial sphere, the radius, and this is kind of your angular amplitude. So the more you start coarse graining, then the more isotropic it looks. In the case of 2 dimensions, this is 1% anisotropies regarding, for example, a property like the coordination number, but you can, of course, choose any other property that you have access to. So I will jump to my conclusions because I think I'm running out of time. We defined quantum gravitational observables capable of determining percentile deviations from perfect homogeneity and isotropy of spacetime. These observables are capable of being implemented in highly fluctuating spacetimes, as the ones that appear in causal dynamical triangulations. We implemented them in 2D, and the results indicate that there could be some residual anisotropies and inhomogeneities in the continuum limit. Again, this is not something physical, it's just a toy model. In the future, we'll implement this in 4-dimensional CDT to actually study the zeta universe that I said at the beginning. And a positive outcome of this would be that the number that we get from our observables tells that this emergent universe is actually compatible with the usually assumed initial conditions for the universe. Thank you very much for your attention, and enjoy your Friday afternoon.
We have time for one question. Yeah, okay. Just a second.
Yes, thank you. This is probably a very naive question, but very nice results. But when
Thank
you
you.
say you're taking the homogeneity inside of a sphere, you don't mean a sphere.
Sorry, this is not.
Okay. Click. Now it makes noise. Yeah. So nice results. But when you say you're taking the distances or counting up the the total number of points inside a sphere, you're not actually measuring a sphere because there's no background, right? This is like a next to nearest neighbor, or like counting the total number of neighbors around a point.
Well, that's how we define a sphere. So we have a notion of distance, a geodesic distance. So in this discrete spacetime, you have, for example, the link distance. So if you start at a point, you choose a radius. You can choose radius 10, distance 10. So you count all the
steps.
all the steps that you
Yes.
take, basically, and you measure. You construct your geodesic sphere as all the points that are at this distance.
Yes. Yes. Cool.
That's what we call a sphere.
Yeah. Sounds good. Thank you.
Okay, thank you very much. Let's thank the speaker again.